All right, everybody, we're going to get started. So thank you for coming to this breakout session where we're going to learn about Bayesian statistics, part 1. Stick around for part 2 afterwards if you're interested. I'll introduce our speaker. Dr. Ting Jhuang holds a PhD in statistics from North Carolina State University. She's developed new Bayesian methods to tackle problems in epidemiology and material science. She is a principal data scientist at United Health Group Research and Development in Minnesota. On a day-to-day basis, she identifies research directions and applies statistical methods to solve scientific and business questions in the healthcare field. Please welcome Dr. Jhuang.
All right, good morning, everyone. So today I'm going to introduce about Bayesian statistics and how to use that in R. So I'll start with talking about the big idea behind Bayesian statistics. So I'm wondering how many of you have heard and also used Bayesian statistic methods? Raise your hand. Well, a lot. Great. Okay, so later I'll move on to important piece of Bayesian statistics as prior types, and also talk about 3 examples in R. All right. So this guy is actually the very important guy in Bayesian statistics. He's a priest of Thomas Bayes, and Bayesian statistics can actually be traced back to the 18th century. So he's actually the founder of the Bayes theorem, which you probably already learned this theorem in high school math. So in Bayesian statistics, actually treat probability as a degree of belief. So it's also a big piece in the prior. And we actually continuously update our prior belief about events as new evidence is presented. So this kind of probabilistic reasoning actually leads to the same kind of results. So it is actually related to interpretation of credible sets, which is a counterpart of confidence interval in frequentist statistics. Okay, so start with the Bayes theorem. It actually centers on the conditional probability. So you can actually view A and B as 2 events. So for example, like A as rain and B as a temperature or humidity. So given today's temperature and humidity, what's the probability of raining today? So you can actually write out as an equation of the probability of event B given A times the probability of event A and divided by the event B. So Bayesian actually comes from this. So I think the biggest difference between frequentist and Bayesian statistics is we actually use posterior distribution to get our conclusion and make inference of our estimators. So developed from the Bayes theorem, you can replace A and B as parameter and data. So here we actually call the posterior distribution as the density of parameter given the observation, the data we have, and it actually proportional to the likelihood. So this piece also occurs in frequentist statistics, but the part which makes Bayesian statistics different is this prior part. So we believe that parameter follows distribution, and we call it as a prior. So I think they will be the 3 big terms in Bayesian statistics: posterior, likelihood, and prior distribution. All right. So this table is sort of a summary of the comparison between frequentist and statistics. So they actually have different interpretation in probability, parameter, and probability statement. So which I'll explain them in the following examples. All right. So talking about prior, there are actually so many different priors in Bayesian statistics. So one of them are expert prior. So for example, like in my previous example, you can use expert prior for the temperature and humidity, but you can also propose on informative prior. So there are actually some different types of prior. So that's about that by reasoning and their features. But like by mass property, you can categorize them into a conjugate prior and non-conjugate prior. So what does that mean? So a conjugate prior actually means it leads to a posterior from the same parametric family as a prior. So this also means we can have a closed form, so it's recognizable distribution, which can make our life much easier when we do the posterior sampling. So the other part is non-conjugate prior. So this part is actually makes your life a little bit harder, but now since we have R, so we can also use a package and function in R. So I'll go through both of them in my following examples. All right. So any questions till now? Okay, so let's start with the first example. So think about like just a very simple coin flip example. And okay, so here we have to introduce our parameters. So let's say that be the probability of having hat and M be the number of tosses. And here the Y is the number of hats and the total number of tosses. So what would be the estimate of theta? So here, traditionally, we use a maximum likelihood estimate to estimate this parameter theta. And we get Y divided by N turns out as the estimate. But what do we do in Bayesian statistics? So in Bayesian statistics, we will start with choose a prior of theta and calculate its posterior distribution, and then use the posterior mean as its estimate. So that's a difference between the frequentist and Bayesian. All right. So here, just a simple proof of we consider a conjugate prior theta is a beta alpha beta beta distribution with the two shape parameters alpha and beta. So given the previous rule that I introduced, you can write out the posterior distribution of theta. It's actually proportional to prior the beta distribution, and the likelihood is a binomial here. So you can actually write out their kernel of distribution, and it will give you a posterior distribution, which also follows a beta distribution. So here we will call this beta prior as a conjugate prior distribution because it leads to the same parametric family of the posterior. So here we actually get the posterior distribution with the two shape parameters alpha plus y and beta plus n minus y. So as you can see here, different from the previous prior alpha beta, it actually incorporates your prior belief and also your data. Okay, so here we will turn out the posterior mean is our estimator. So it's actually this ratio. Okay, so here is that the thing is, previously we talked about like the proof and how to get a Bayesian estimate. And now it's go through that in R. So here, some setup of this example is here, and is number of tosses, and here imposes just the size of the posterior sample. And y is a number of heads, and alpha and beta, I set up them both at 2 here, and you can always change as the value what you want. So the next step is to specify our prior and likelihood. So in R, it's pretty easy that you can just use a random sample of beta and also binomial to make a plot of prior and likelihood. All right. So here, this figure 2, it actually shows our prior belief of theta. So you can see it actually, if you believe, so I propose this prior because I believe this coin is fair. So you can see it actually, the highest point is around 0.5 here. But like in beta distribution, you can also have some other shape like U shape or like some other shape of beta distribution. And how you propose a prior actually reflects your belief. So here I believe it's a fair coin, so I'll just put as alpha and beta as 2. And the likelihood of y here is actually, you can see it centered here. So, okay. So the next one, we draw a posterior sample after we specify our prior and likelihood. So the first one here, the theta posterior sample here is actually, you draw the number m post means the sample size of your posterior sample and the 2 new shape parameter and your posterior distribution. And the following code are just plotting the posterior sample. So here you can see, you can hardly see the dark green here since the maximum likelihood estimates and base estimate, they are actually pretty close to each other. So I think that also usually not always, but usually happens when you have a conjugate prior and posterior. It usually leads to a very similar results in frequentist and Bayesian statistics. All right, so the previous example I talked about is a pretty easy one, a coin flip and with a conjugate prior and posterior. So now think about if we don't have this kind of conjugate prior, what do we do? All right, so for example, like in just a normal logistic regression model, and you have only one predictor. So what will you do for the Bayesian statistics? So if we have a normal prior, so a normal prior is a very usual setting for the prior for a regression coefficient. But here now we have the logit length function. We don't have a continuous y, so we don't have conjugate prior. So here, write down the formula. The posterior actually is proportional to the likelihood, the p here, and also its prior, the normal density here. So actually, like from this formula, you cannot find any parametric distribution, to draw a posterior sample from. So obviously we cannot use the same technique previously for this one. Okay, so what do we do here? So I think the same part is that we will start as a select a model and prior, but the different thing is we will approximate our posterior using MCMC, which is Markov chain Monte Carlo, and is a very important piece of Bayesian statistics. And then the third step, we will check the posterior approximation and finally use our MCMC samples to make any inferences. So for MCMC methods, there are two ways. So you can code it on your own, which I did in my PhD, or you can directly use our packages, which already have so many functions, and you can just specify your likelihood and posterior, and it will draw the posterior sample for you. Okay, so let's see like how this MCMC sampling actually works. So first, we have to choose a starter to let it run. So it's actually an iterative process. So you have to like put something in and let it run. And then it will iterate between actually for the two steps. So in each step, it will actually propose a new value based on the current parameter value. And then you can choose to move to a new value or I stay here. So that's sort of the general idea of MCMC. Of course, there are many variants of this MCMC sampling. Okay, so there are two packages I want to introduce today for the MCMC sampling. So the first one is called MCMC. It's actually more general. You just have to specify the posterior density and you will calculate the posterior for you. And the other one is MCMC pack, which I will use that for my following example about the linear regression. So it actually has a similar function as what you use for frequentist statistics, the LM function. So you have like similar ways to specify the function and you can get what you want here. All right, so let's see an example of non-conjugate prior. So actually here, you have to install MCMC package first. And then there is a data called logic there directly in their package. And here, why I want to have the out here is I want to use the estimate from the frequentist model as my initial values. So here, actually, you can choose initial values on your own, and like you can choose many different values. But I mean, in my experience, like the maximum likelihood estimates are usually good initial values to have a reasonable posterior sample. So here, the middle chunk of here, the log density posterior here is the way we specify the log posterior density. Okay, so the next step after writing out this is to construct the log posterior density here and beta initial. So here I use a SSD just for reproducible results. So beta initial here, I actually use the regression coefficients from the frequentist methods. And then you only have to use this function, the Metrop. So Metrop actually represents Metropolis algorithm. So it's very basic one in MCMC sampling. All right. So after this, you can make we call this as a trace plot. So you actually have, so here, like here, the 1,000 means that I have draw 1,000 times. So in my posterior sample for the beta now and beta 1, I'll have 1,000 values. And here is just like by each iteration, I make a trend plot of it. So here it means the trace plot of beta null, and this is a trace plot of beta 1. All right. So any questions till now? Great. Okay. So the last example we will review is bike share data set. So it actually records the daily and hourly count of rental bikes between the 2 years in capital bike share system. And it also has some information, weather and seasonal information. So our objective here is to decide if fuel light temperature is related to the number of registered riders. Okay. So here it is a scatter plot in ggplot2. So as you can see, it actually shows a strong linear and positive linear relationship here. So we think that it's reasonable to fit a linear regression model. All right. So here just the model form, and the different piece is here the prior specification. So usually we will specify a normal prior for the regression coefficient, and for the random error part, the variance here, we usually have inverse gamma distribution. So the reason why we have this kind of specification is to make your life easier, since by this kind of setting, you will have a conjugate posterior. So you don't have to write your own MCMC sample. Okay. So here we fit the models in 2 ways. So we actually got the frequentist way and the Bayesian way. So I think for frequentist, I don't have to mention too much. It's just a normal LM function. But for Bayesian fit, you can use the MCMC regress function in MCMC pack package. So MCMC pack package is actually a very strong and powerful package for drawing posterior sample. You can actually do this, and there are also many other ones, and you can also examine how your posterior sample looks like, and if it makes sense, and if it converges, and it also contains some other statistics, which Christina will introduce later on. Okay, so I'll explain what I did for this function. So for the model specification, it's still the same as the LM function. And here the little b0 and the big B0 is the initial value setting. So they are actually the initial value setting for your beta, your regression coefficient. So if you don't specify here, it will use, this function will use its default. And here the sigma mu and the sigma variance, it's actually the mean and the variance for the inverse gamma prior for the sigma square for the random variance part. Okay, so here the last line is the Bayesian and MCMC. So MCMC here is just the number of the size of posterior sample you want to have. So you can actually have 10,000 or even more, a million. And Bayesian here is actually a one that the idea is to discard the first several samples. So the Bayesian here I specify as 1,000 is that, so I'll actually discard the first 1,000 posterior sample I have. So this function will actually draws 1,000 plus 10,000 posterior example, and I just discard the first 1,000 one. So I'll use the remaining one.
Is that because your initial values?
Yeah, exactly. So the reason why I want to have burn-in is that sometimes, yeah, you're right. Sometimes it will take some time. So just like if you drive a car during the winter, you need some time to warm up. So that's actually the same idea for the MC trend to discard some before you draw any conclusion from your posterior sample. Because as we know, we use the posterior mean as an estimate. So mean actually is heavily affected if you have any outlier. Yeah, so that's why we'll have initial.
Quick question. So you have the small b0 and big B0 as the initial values, but I'm not sure I see where the prior distributions would go in here. Like, don't you have to have a prior distribution for those betas as well?
Yeah, sure. So the thing is that this function, they have default setup. So the little b now and the big B now here, they are actually the parameter specification of a normal prior. So they actually assume that those beta regression coefficient, they have a normal prior, and random error variance, they have an inverse gamma prior. Yeah.
Can I ask a question? Sure. The ratio or the number of burn-in sort of iterations that you do, is there any magic to picking that, or do you just make sure you just have like some robust number that comes in?
Yeah, so it's actually no rule of thumb of that, but I mean, what I do is that I usually have a trace plot and to see their trend and to make my final decision. Because sometimes I think for this kind of have conjugate prior and posterior thing, it doesn't matter too much. But if you don't have a conjugate posterior, then you have to be very careful about like for different initial values and how many I have to burn in before I get a robust result.
But that would be your process. You would look at a plot to see kind of at what point it begins to stay.
Exactly.
And then you pick a number that's around there.
Yeah.
Yeah. Thank you.
Great. Any other questions? All right. So we actually got very similar results for these two models. Okay. So to go back to our objective is to decide if these two, they are significantly related. So for this, I think you're already very familiar with the hypothesis test. It's to actually find out if this coefficient is 0 or not. And this is the output from the frequentist regression. So we can directly find out here, but what it will look like for the Bayesian statistics. So if you use MC package and use the MC regress function I mentioned, it will actually give you these two parts of the output. So here the iterations are actually from 1,001 to 101,000. It actually means it already discards the first 1,000 sample and use the remaining one. And so here we only use a number, like we use one trend. So you can specify different number. You can have different trends to have your posterior sample. And the sample size per trend here is the 10 to the power of 5. So here we can see there are actually the similar output results of this your estimate. So here is your beta 0 and the beta 1 and the sigma square is your random error variance. And then the second part, it actually your quantile of each variable. So it actually gives you also a 5-number summary of your posterior sample. So here, for example, like for the 50 percentile is a median. So it actually means this one is the median of your posterior sample for sigma square. Okay, so in this slide, I want to talk about the different interpretation about the inference for this beta 1, the slope. So we actually can get the results from frequentist and the Bayesian models. And in frequentist, we call it as confidence interval. So it actually a repeating procedure concept. So it actually means once I get a 95% confidence interval, it means that I am 95% confident that beta 1 locates in this interval. So it actually means if I repeat this procedure for 100 times, then about 95 of them will include the true parameter. And so it's also a different concept that frequentist views this beta 1 parameter as a fixed but unknown number. But in Bayesian, we do view a beta 1 as actually a random variable. It actually follows a distribution. So we interpret the credible set differently as the probability beta 1 locates between these two numbers, the probability is actually 0.95. So it's a different thing for frequentist and Bayesian.
One thing I always wondered is, are all frequentist models the same as Bayesian models with an uninformative prior?
Not really. I'll say it depends. Yeah, but I'll say for those settings with conjugate prior and posterior, you will usually get the same results. But for other, like using Metropolis or other more complex MCMC sampling, then sometimes you will have different results. And also it's related to how you set up your initial values and how you propose your prior. They are all, they can all lead to the different results. Yeah. All right. So like I just introduced about the example for the Bayesian statistics. So it actually treats probability as a degree of belief, which I think it's it's very intuitive that like you make any decision. So like if I have to bring an umbrella today when I go out, so I actually will have some prior, like, so I think like it ran yesterday, or I have some prior information to decide if I have to bring an umbrella today for out. And that's, the biggest difference between frequentist and Bayesian is the way we treat a parameter. So there actually, I think prior is actually a pretty important piece in Bayesian statistics. So we don't have time to go through many types of them, but I'll say domain knowledge and sensitivity analysis are very important to decide a prior and also to have your results making sense to others. And the other thing that I usually do is I'll calculate also in frequentist methods, and I'll compare their results and to see if they are consistent. So here the sensitivity analysis I mean is that I'll try different priors or like different initial values or different algorithm to see if it leads to very different posterior samples. So lastly, R is your good friend for Bayesian statistics. So I think Bayesian statistics become more and more popular because the advance in computers. So now like you can draw a posterior sample very soon, but it was not that fast about decades ago. So it also closely tied with the development of this computing power. All right, so I think that's all for my talk today. Thank you very much.
Time for a couple questions.
Can you go to slide 21? So this may have been the same question you asked, but we have the betas are normally distributed at 0, around mean 0 and variance 100.
Mm-hmm.
And then on the next slide,
Mm-hmm.
you're saying that is the
Here, this part.
Well, yeah. So where do we specify? The
Oh,
variance?
yeah. So here it actually, are you asking about the difference between 100 and 0.01? Or
Well, I guess I'm seeing, where are we specifying the prior, I believe, the variance around the beta? So
Oh,
where is that-
okay.
where am I-
Yeah, so here I actually treat the variance of beta as fixed.
Okay.
Yeah, so here you will see it's 100 here, and here it's actually it's a reciprocal of variance. So here I put that as 0.01. So in this function, it automatically sets the prior for the regression coefficient as a normal prior.
Okay.
Yeah.
So compared to the frequentist method, what's the advantage and disadvantage of the variance method? It's based on your personal experience. In which area or which situation, Bayesian method will generally outperform the classical method?
Mm-hmm. So I think the major advantage of Bayesian statistics is that you can always update the posterior sample once you have newer data. So it actually sort of like a machine keeps going on, and I think that's the benefit of Bayesian statistics. And also the other case is, in some case, it's hard to calculate a maximum likelihood estimate of a model, but we can do that in Bayesian. So I think that's I think it still depends, I mean, like case by case, but they're I think the two advantage I think Bayesian has other than the frequentist method.
Yeah, I actually have a question that to me is Bayesian statistics is much less intuitive than frequent statistics. So if you want to supply your output or your process to a person who doesn't have any idea about Bayesian statistics or even statistics, how do you convince that person your output is right? Or
You mean like the way that we treat parameter and like the whole?
Yeah, because during this process, many of the steps seems like it's just a judgment call. You choose how you choose your distribution, how you choose your beta, how you choose your prior, or how you choose your likelihood. So how do you convince those persons who doesn't have any idea about it?
So, well, I mean, like, to be honest, to me, I actually feel it's sort of just like religion thing, since that the way that you treat, actually, I actually think both frequentist and Bayesian, they have different strengths, and sometimes either one can be better than other one, but I think the idea is that both of them provide us the tools that we can solve the problem. Because I mean, if you don't believe that, then it's actually impossible for me to convince you that, oh, hey, this is very good, just like different species of apples, and like I have to convince you that, oh, hey, this Honeycrisp is very great, but you don't believe that. So yeah, that's my opinion about this.
And to add on to that, like when you do frequentist statistics, you make all sorts of assumptions, like, okay, let's assume the residuals are normally distributed, or let's assume this or that.
Yeah.
And most frequentists are just like, yeah, okay, that's fine, we'll assume that. So it's like, okay, which thing do you want to just like, all right.
Yeah.
So we better break here in case people want to switch down to the other session, but you can follow up with Ting afterwards or stick around for Bayesian part 2. Thank you.
All right, thank you.